Hello, everybody. Welcome to our video here for AP Pre-Calculus. This is Coach Meidenbauer, and let's get rocking and rolling this thing here. So we got topic 1.1, change in tandem. So essentially, if you read this entire box right up here, it's going to focus on a couple things, just really vocabulary-wise. What we need to know is our x's are our input values. So you'll be hearing that vocabulary a little bit more often than you previously have. So x is our inputs, and this also relates to our domain values. And y's are our output values, which relates to our range. So for every single x, which is input, there's going to be some type of output value for any type of function that we have. Okay. So let's go ahead and look at this table down here. And these are four different representations of functions. We have analytical, graphical, numerical, and verbal. So the first, we'll start with analytical. We have this function here, which is going to be 200 plus 10x. And that's actually going to relate to a bunch of these other parts on our table. So we're going to use this function for that and for that down there. If the input value is 5, what is the output value? So you need to know that this means, well, x is equal to 5. What is y equal to? Well, we do know that y is the same thing as f of x. So what we're trying to find is f of 5. Okay? So we need to find f of 5. So all we're going to do is we're going to plug in 5 into our function right here, 200 plus 10x. So 200 plus 10 times 5. That's going to equal 250. Okay, so that's the analytical representation of a function using input-output values. For the next one, for graphical here, we're going to graph the point with an input value of 5. So 5 is right here, by the way. So if we just kind of look up, we get this point right here. And this is going to be the point 5, comma. Again, it relates back to this function over here. It's going to be 5, comma 250. And as you can see, the height, 250. Numerical, that's going to be on the bottom left there. Complete the table of values. Again, we're going back to this function. This table of values, if 0 was 200, we're increasing by 10 every time. So this is going to be 210. When we have 1, when we have 2, we're going to have 220. We have 3, we're going to have 230. We have 4, we're going to have 240. Last one here is going to be verbal. There are 200 people in a small concert venue. The gate allows 10 people to enter every minute. Write a function in terms of t, where t represents minutes and c of t represents the number of people at the concert venue at any time t. So it's important to note here that we're going to have variables of t now, and then we're going to have c of t. So t is going to be my input value because we're inputting these people that are going to the concert, and the number of people is going to be my output. And let's be consistent with the letters and everything that we're doing here. So we have 200 people that are in a small concert venue. So we start with 200. We're in 10 people at a time, so plus 10 t. Okay, and this is what c of t is equal to. That's all they ask is just what does this function represent. Okay, moving on. Okay, we're going to talk more about technical stuff that you probably already know or been talked about, especially with increasing, decreasing. I mean, you can look at a function and know, hey, it's increasing here, it's decreasing here, but technically why? So if the graph intersects the x-axis, then the output value, when the output value is 0, then we said that there's those zeros of the function. Okay, so look down here in this function right here. We have a 0 right there, which looks like it's going to be at 1.5. So that's a 0. Same thing right here. That's a 0 right there. Looks like that's 1.5 as well. Those are zeros. A function is increasing over an interval on its domain if the input values increase and the output values increase. Okay, so what we're trying to say is if the value to the right of it is getting higher, we're increasing. Okay, that's the technical mumbo jumbo, and that's why it says for all A and B where A is less than B. So if A is here and then B is higher than it, it's increasing, and that's if it happens at every single point on that domain. Okay, and then increasing function, you can see it right here to the left, and you can see that decreasing, same thing, with the input value increasing, but the output value is going to decrease. So as long as every point afterwards down the number line is getting smaller, then we're decreasing. So here's a true false for this piecewise function right here. So f increases from -5 to -2. Okay, not including -5, not including -2. So if you look, we're starting here and we're going down the entire time. There's a hole there. That's not going to concern me because the hole's at -2, but we are not equaling -2. So is this decreasing? Yes, that's going to be true. So put a T for true. F increases from 0 to 2. So it's going to be this part right here. Okay, actually, I'll do that different color. I'll fix that. So we're increasing from 0 to 2. That is totally true. Looks like it's increasing more. We get closer to 2, not increasing quite as fast when we're close to 0. What about increases from 0 to 5? It's kind of a different one for us. So from 0 to 5 will be this part right here. Now, it looks like a little corner right there, but is every single part of the function from 0 to 5, is the left part always smaller than the right part, no matter what left part we pick? Yeah, totally. So that is true. F decreases from -2 to 2. Well, I agree that we're going to decrease a little bit here. We're going to decrease right there, but since I increase anywhere on this interval, it's untrue that it decreases on the entire interval. So this is going to be a false. Okay, and then last ones here is going to be that we have zeros at plus and -2. Well, we touch the x-axis there and there, so that is most certainly true. Okay, nothing should be new here. We're just kind of getting back in the flow of things here for pre-calculus. That's going to be something that isn't going to be new unless your Algebra 2 teachers talked about it. We're going to talk a little about concavity. Oh, boy. These technical difficulties. There we go. So the graph of a function is concave up if the rate of change is increasing. So now rate of change is going to be how is the graph changing. So an easy way to remember this for concave up is that we're going to be up like a cup. Up like a cup. It can hold water. So if you look at our example here for concave up, the entire function is the rate of change is increasing. What the heck does that mean? Well, if I were to draw a tangent line to the graph like this right here, that's the average rate of change on this point, or near approaching that point. That slope actually starts to increase as I get further down the function. Okay, so here we're very negative on the far left. We're very negative. Then we get less negative. Then we get 0, and then we get positive and more positive. That's what concave up is. The rate of change is increasing. Now, the rate of change is decreasing, or concave down, when we look like a frown. So this will be down like a frown. down like a frown. So this is when our rate of change is decreasing. So here we're very positive, we're less positive, we're zero, we're negative, we're more negative. So we're concave down, really down like a frown is the way to remember it. But if our rate of change is decreasing. Okay, here's our last part here, last example. So we have another piecewise function. It looks like a couple of parabolas, and looks like maybe a semicircle there at the end. So we're going to talk about from 2 to 6 right here on that semicircle looking part of this function. G increases from 2 to 6. Oh, I'm in a room that light turns off. So here, are we increasing on part of it? Yeah. Are we increasing on all of it? No. So that's going to be false. G is concave down from 0 to 2. Well, that looks to me like that looks like half of a cup, up like a cup. So that's going to be false. We're actually concave up there. G is concave up from -6 to -2, which is right here. I would say that is totally true. Up like a cup. 4, I have two conditions on 4. It says that G is decreasing and we are concave up. So I already traced it from, actually, I didn't do this one yet. -2 until 0. So it's right there that I'm tracing. So are we decreasing and concave up? Definitely decreasing. And it appears that we're concave up as well. So that is true. 5 talks about our zeros. Let's look at our zeros. We have a 0 here at -6, at 2, -2, at 2, and at 6. So that is certainly true for our zeros. Last but not least here, G is decreasing from -6 to -4. Do that in gray. From -6 to -4, which is right here. I'm decreasing on a decreasing rate. What the heck does that mean? Well, come back up to our concavity here. Decreasing rate is concave down. So this is the same thing as concave down. So it's important to know these vocab words. So are we concave down here? Nope, we're concave up, so this is going to be false. Okay, and that wraps up this lesson. If you enjoyed it, please click like the video and subscribe. And that's it.